Welcome all. We are going to learn about coordination compounds. What are coordination compounds? The compounds which retain their identities even when dissolved in water or in any other solvent where the properties are completely different from those of the individual components are called coordination compounds. For example, nickel hexaamine chloride. This is a compound which, when dissolves in water, you can see that it gets separated as chloride ion and complete a complex ion. Similarly, cobalt hexaamine chloride. While nickel hexaamine chloride can be called as a coordinate compound. Let's see. As it is formed by following process. First, when aqueous ammonia is added to a green solution of nickel chloride, the color changes to purple. The nickel ion almost disappears from the solution and ammonia enters into an intimate association with nickel plus 2 to yield a new ion, nickel hexaamine plus 2. This ion is also called complex ion. On evaporation of this solution, a purple crystals of above formula is produced and hence it is called as a coordinate compound. Now, if this compound is dissolved in water, there is no evidence for the existence of free nickel ions or ammonia molecules. The property of the complex compound is entirely different from those of nickel ions or ammonia molecules. Hence, this compound is called a coordinate compound. Coordination compound is equals to complex compound. This compound ionizes in solutions as with a complex ion plus the chloride ions, that is N ions. Nowadays, a large number of complex compounds of different types are known, like a precipitate of silver cyanide, when dissolved in solution of potassium cyanide, gives a soluble coordination compound known as potassium dicyanide or we can also simply say as potassium silver cyanide complex. Now, what is complex chemistry? The branch of chemistry that deals with the study of coordination compounds or complex compounds, termed as complex chemistry. The complex chemistry is really not that complex. Why do transition metal compounds forms complexes? Why not other metals in a periodic table tends to form complexes? Let's quickly get the solution. The transition metals are almost unique in their tendency to form coordination complexes. The tendency of cations of transition elements to form complexes is due to two factors. These ions are very small in size and therefore have high positive charge density. This facilitates acceptance of lone pair of electrons from other molecules. They have vacant orbitals and these orbitals have the appropriate type of energy to accept lone pair of electrons. What is a coordinate bond? We have already studied in our lower grades different types of bond formation taking place between the two different atoms or ions, say ionic bond, covalent bond, hydrogen bond. So now again let's revise what is a coordinate bond. When both the electrons are being shared between the atoms are contributed by one atom only, then this type of bond is called coordination bond. It is also called dative bond. Basically, you can recall an example of coordinate bond as ammonium chloride, where ammonia is formed and then the lone pair of electron of nitrogen is completely donated to the hydrogen ion. A coordinate bond established between the two atoms, one of which has a complete octet with at least one pair of unshared electrons, while the other is short of two electrons. Example, here you can see we have taken an example of formation of H3O plus ion. Right here we have a water molecule. Oxygen is having two lone pair of electrons and it is reacting with hydrogen ion. So oxygen is ready to give its lone pair of electron to the hydrogen ion and hence we form a coordinate bond which is been shown by a arrow. So formation of hydrogen ion from water molecules is also an example of a coordinate bond. Terms that are useful in explaining coordinate compounds. First of all, complex ion. What is a complex ion? An electrically charged ion which consists of a central metal atom or ion surrounded by a group of ions or neutral atom is termed as complex ion. For example, nickel hexamine plus 2 is a complex ion in which Ni2 plus is the central metal atom surrounded by 6 ammonia molecules. Central ion and ligand, which again plays a very important role in identifying the complex. The cation to which one or more neutral molecules are coordinated is called the central ion, and the attached molecules are called ligand. Hence, in a nickel hexamine complex ion, Ni2 plus is the central ion surrounded by ammonia as a ligand. Coordinate number, which is also known as coordination number. The total number of ligands attached to a central metal ion or atom is called the coordinate number of that particular ion. For example, CuNH3 4 2 plus, here the coordination number of copper is 4 as copper is attached with 4 ligands. Coordination sphere or coordinate sphere, the central metal ion together with the molecules or ion coordinated to it is termed as coordination sphere. The sphere that is placed between the square bracket. So for example, your silver cyanide minus is a coordinate sphere. Even over here, CuNH3 4 2 plus is also come under the coordination sphere. Ions and ligands coordinated to it. In complex ions, CuNH3 4 2 plus. Cu2 plus carries a charge of positive 2 and ammonia molecule is neutral. Hence, the total algebraic sum of these two are plus 2. Thus, CuNH3 4 carries a charge of plus 2. Right, because we know copper is plus 2, here it is 0. Hence, the overall complex is getting a charge of positive 2. The species within the square bracket are coordination entities or complexes. And the ions outside the square brackets are called counter ions. It can be a positive ion or a negative ion. Let's have a look how ligands are classified. A ligand contains one or more than one donor atoms for coordination with the central ion. I repeat, a ligand contains one or more than one donor atoms for coordination with the central ion. Accordingly, which is classified below as an unidentate or monodentate ligand. Unidentate or monodentate ligand means the ligands which can provide only one coordination site. It is known as unidentate or monodentate ligand, for example, ammonia, water, chloride, bromide, Na2 minus, etc. Next, bidentate ligand, which provides two coordination sites. The ligands which have two donor atoms and hence they have the tendency to attach with the central ion through two donor atoms are known as bidentate ligand. For example, ethylene diamine. Here both the nitrogen of the amino group have the lone pair of electrons through which they can attach with the central metal ion. And again, oxalate ion you can see which is formed by releasing the hydrogen ion of the oxalic acid. Polydentate ligand termed as the ligands which coordinates with the central ion through more than two donor atoms present in the molecules are called polydentate ligands. For example, EDTA, the full form of EDTA is ethylene diamine tetraacetic acid, which is an important hexadentate ligand because it can provide six coordination site and hence it also comes under the hexadentate ligand. It binds through two nitrogen and four oxygen atom of the 4 carboxylic group to the central metal ion. And this is, you can see, it's a structure of ethylene diamine. So kindly just make the basic structure of ethylene diamine and then the hydrogen atom of the amino group is replaced by the carboxylic group, that is acetic acid. Next, chelating ligands and chelates. When a bidentate or a polydentate ligand is attached through two or more donor atoms to the same central metal ion to form a ring structure, the ligand is thus called a chelating ligand and hence the resulting complex formed so is called a chelate. Here we have different examples. M, it can be any central metal ion of the transition metals, that is the D block metals. So here the example is for ethylene diamine, which is having two coordination sites and both the coordination sites is attached with the central metal ion. And here we go with the example, that is copper ethylene diamine bis ethylene diamine because two ethylene diamine is there. So organic ligand, so we use bis instead of di. Now let's check how to give IUPAC name or nomenclature to the coordination compounds. We need to take care of few things, that is within the coordination entities. The central atom or ion is listed first, followed by the ligands. The ligands are then listed after the central metal atom or ion in alphabetical order. The formula of coordination entity is written in square brackets. Ligand abbreviations are also written in parentheses. There should be no space between the ligands and the metal within a coordination sphere. The charge on the cations is balanced by the charge of the anions. Rules for IUPAC nomenclature. While naming a coordination compound, cations is always named before the anion, irrespective of the fact that whether the complex ion is cation or anion. For example, over here we have a positive ion before the complex. Okay, that is the coordination site where we can say a central metal ion is attached with the ammonia and Cl2. So Na is to be named first, followed by, right? So it is known as sodium tetraamine dichlorocobaltate 1. I repeat, sodium tetraamine dichlorocobaltate 1. Sodium is to be named first allowed by the complex, hence it is named as sodium tetraamine dichlorocobaltate 1. Now as you can see here, cobaltate, that is Cobaltate, cobaltate. And next is your followed by tetraamine, that is tetraamine dichloro cobalt 0 sulfate. Now, how it is so 1 and 0? That is due to the oxidation number. We represent it in the stock notation. The stock notation is used as in numerals, Roman numerals. Next rule is if there are more than one type of ligands present in any coordination compound, the name of the ligand is to be done in alphabetical order, followed by the name of central metal atom or ion, name of the anionic ligand ends with O. For example, chloride, it will be named as chlorido. Nitrate, it will be named as nitrito. For neutral ligands, their common name are used as ethylene diamine, water aqua, NH3amine. Can just check the spelling. Amine is AMMINE, whereas in ethylene diamine we use only single M. So kindly take a note of it. CO carbonyl, N2 dinitrogen, O2 dioxygen. These all are comes under the neutral ligands. So it's very, very important to know which ligands are coming under neutral ligands. Here comes your anionic ligands with your name, that is bromide ions, so it is bromo, fluoro, oxo, hydroxo, cyano, oxalato, carbonato, aceto. Whereas your neutral ligands are also lying over here. So do take care of your neutral ligands. Next, if the names of the ligands already contains a numerical prefix, then the terms bis, tris, tetrakis and are used and the ligand into which they refer being placed in parentheses. For example, your NiCl2 and this is P for phenyl and pH3 is your phosphine twice is named as dichlorido bis triphenyl phosphine nickel 2. After naming the ligand in alphabetical order, name the central metal atom or ion is written. If the complex ion is a cation, metal is named same as the element. And if the complex is an anion, the name of metal ends with the suffix "ate" for Latin name. Here you might have seen in the previous slide, somewhere we have written cobaltate and somewhere only cobalt. So these are again the names of the metals, Latin name and anion name. The oxidation state of the metal in the complex is given as a Roman numeral in parentheses, as I told you earlier. The neutral complex molecule is named similar to that of the complex cation. These are some ligands which may be attached to the central metal atom or ion through different atoms. For example, NNO2, which is known as nitro, but if it is attached with the oxygen as an ligand site, it will be termed as nitrito. If it is SCN attached with the S, it is known as thiocyanate, and if it is NCS attached with N, the metal atom or ion is attached with the N, this is known as isothiocyanate. Now, these ligands are also called as ambident ligands as it's have more than one site to attach with. As in your previous chapter, you have learned about ambident nucleophile. So these are the examples of ambident ligands, or we also call it as ambidentate ligands. Now, few examples that you can solve so that you can apply and confirm the IUPAC rules for giving a name to the different complex compounds. What actually Werner's talk about the coordination compound? In 1893, Werner proposed a theory to explain the structure and bonding in coordination compounds. In coordination compounds, metals show two types of valencies. First, primary valency and secondary valency. Primary valencies are ionizable, whereas secondary valencies are not ionizable. This theory, Werner's theory, was successful to very limited extent and could not explain many aspects of coordination compounds. With this example of complex ion, you can check that where it is, where the primary valence is, and how it is been explained. The ionizable anion, that means they are the primary valencies, whereas the one which cannot ionize, it is called as secondary valency. So secondary valency of a metal is equal to the number of ligands attached to it. That is the coordination number. Hence here, this is the central ion, which is your copper, sorry, which is cobalt, that is CO2 plus, which give attached with the 6, which attached with the 6 ligands, that is 2 chlorine and 4 amine. And primary valencies are satisfied by negative ions, while secondary valencies may be satisfied by neutral, negative, or positive ions. Secondary valencies have a fixed orientation around the metal in space. So in this, we can come to know that how the primary valencies and secondary valencies has been calculated. So in this complex, the primary valency, which is 3, and secondary valencies is 6, as the coordination number is 6, and the coordination sphere is CONH363 minus. Sorry, it's CONH363 plus. Coordination sphere is 3 plus. CONH363 plus. Isomerism in coordination compounds. This is for timing not there in your syllabus, but just for an example, we do have two different types of structural different types of isomerism, that is structural isomerism and stereoisomerism. Structural isomerism is further classified into chain isomerism, position isomerism, functional isomerism, metamerism, tautomerism, ring chain isomerism, whereas stereoisomerism is geometrical isomerism and optical isomerism. Now let's see few examples how structural isomerisms have again subtypes, that is ionization isomerism, exchange of ligands between the coordination sphere and ionization sphere. We have the different examples, whereas in hydrate isomerism, exchange of water molecules between coordinate sphere and ionization sphere. We have linkage isomerism where ambident ligands binds from the different binding sites. Ambident ligands binds from the different binding sites to the metal atom. Coordination isomerism, exchange of the metal atom between the coordination sphere and ionization sphere when both are complex ions. Ligand isomerism, that is the different isomers of the same ligands attached to the metal. You can see stereoisomerism, that is geometrical isomerisms, which give rise to cis and trans isomers. When two similar ligands are on the adjacent position, the isomer is called cis isomers, whereas when they are on the opposite positions, the isomer is called trans isomerism. Optical isomerism, in order to show optical isomerism, the complex should form a non-superimposable mirror image which rotates the place of polarized light in opposite direction. Next come valence bond theory, which is also known as VB theory. In this theory, it has been told that is the strong field ligands cause the pairing of electrons. Now, what do you understand by strong? Few examples of strong field ligands and weak field ligands. They have been placed when the d orbital taking part in hybridization is inside the s and p orbital taking part in hybridizations with respect to the nucleus. It is called an inner orbital complex. Later we will be seeing how the inner orbital complex is been taking place. For example, D2sp3 hybridizations for cobalt hexamine complex involves 3d and 4s and 4p orbital, hence it is an inner orbital complex. Now when the d orbital taking part in hybridization outside the s and p orbital taking part in hybridization with respect to the nucleus, it is called an outer orbital complex. Example, sp3d2 hybridizations involves 4d, 4s and 4p orbital, which is known as outer orbital complex. So this is an example of inner orbital complex and outer orbital complex. You can see here how and why, that is depending upon the type of ligand it has. Here it is an NH3 6 ligand, right? As this is a strong ligand, so the pairing takes place and hence it gets a inner orbital complex to undergo the hybridizations, whereas your F fluorine, it is a weak ligand, so pairing does not take place in the 3d orbital, hence it has to undergo the outer orbital complex hybridization. So this is what, depending upon the geometry, the hybridization, or the depending upon hybridization geometry takes place, vice versa. And for coordination number 4, that means the metal complex type Ml4, we have two possibilities of geometry as well as the two possibilities for the hybridizations. Whereas for coordination number 6, again we have two different types of hybridization possibilities depending upon the inner orbital complex and outer orbital complex, but the geometry is octahedral only. Magnetic properties, diamagnetic, all the electrons are paired. Paramagnetic, contain unpaired electrons in its hybridizations. During the time of hybridization, spin paired means all electrons are paired. Spin free contains unpaired electrons, whereas compound must contain free electrons in order to show the color of the complex compounds. Crystal field theory, which is also known as CFT. Crystal field theory also talks about the strong field ligand as well as weak field ligand with respect to its strength and with respect to its relative strength. So this is the order of the strength of ligand as follows. That how we can come to know that whether the ligands are weak ligands, strong ligands or neutral ligands. Next, octahedral complexes are the complex where Eg orbital are of higher energy than T2G orbital, as they split the degenerate d orbital splits into the two suborbitals, that is Eg orbitals in octahedral field directly face the ligands. Now what are Eg orbitals? The orbitals in octahedral field that directly face the ligands, they are termed as Eg orbital. Hence, due to the strong repulsion between the ligand field and electron in this orbital raises its energy. Whereas T2G orbitals are not directed towards the ligand field, hence though the energy increases from the earlier degenerate level, it will be less than the Eg level. Tetrahedral complexes, your Eg orbitals are of lower energy than the T2G orbitals. Few questions you need to solve to know the color, why they are acting as an oxidizing agent. So, why is hydrochloric acid not used to acidify a permanganate solution? Is volumetric estimations of Fe ion and oxalate ion. Next question, why is copper sulfate pentahydrate color? Kindly go with the solutions given below. As it contains 5 water molecules into it. From the white light falling on it, red wavelength is absorbed or excitation of electron from lower to higher energy level takes place. Next, very important questions. Most of the transition metals do not displace hydrogen from dilute acids. Reason? Because of the transition metals have negative oxidation potentials. Do you know K2PT, that is potassium, um, platinum hexachloride complex is well known compound, whereas corresponding nickel compound is not known because PT4 plus is more stable than Ni4 plus. Next, why have the transition elements have high enthalpy of hydration? Because of their small size and large nuclear charge. Though copper, silver, and gold have completely filled sets of d orbitals, yet they are considered as transition metals because these metals in their common oxidation states have incompletely filled d orbitals. Next, few more detailed about the inner orbital low spin complexes with their examples. Outer orbital or high spin complexes with few more examples. This is what we are talking about crystal field stabilization energy, which is your CFSE. Magnetic properties. Now, what are the assumptions of crystal field theory? The ligands are assumed to be point charges. As per crystal field theory, the interaction between the point charges and the electrons of the central metal are electrostatic in nature. The 5d orbitals in an isolated gaseous metal ion have the same energy, that is, they are degenerate levels. The stability of a coordination compound is measured in terms of its stability constant. Drawbacks of crystal field splitting. From the assumption that ligands are point charges, it follows that anionic ligand should exert greatest splitting effect. But anionic ligands actually are found at the low end of the spectrochemical series. It does not take into account for the covalent character of bonding between the ligand and the central atom. Bonding in metal carbonyls. In metal carbonyl, the metal carbon bond possesses both the sigma and the pi bond character. Importance and applications of coordination compounds. Coordination compound is useful in many quantitative and qualitative chemical analysis. extraction processes of metals like silver and gold. Purifications of metals like nickel can be achieved through formation and subsequent decomposition of their coordination compounds. In biological systems, the pigment responsible for the photosynthesis is chlorophyll, which is again a coordination compound of magnesium. Hemoglobin, it's a coordination compound of iron, acts as an oxygen carrier, useful as a case of chelate therapy in medicinal chemistry. Thank you. Have a nice day. Stay safe. Stay fit.